Hello everyone, my name is Brethauer and I'm a fifth-year graduate student here at UC Berkeley in the Astronomy department, and today we'll be rocking out to some heavy metals and we'll be discussing my research into the origins of the heaviest elements in our universe. So before I begin, what exactly are these heavy elements? So these are things like gold that's in your jewelry. Perhaps if you took a car or a bus to work today, there's iridium in the spark plugs for those engines. There's iodine that's mixed in with table salt, so perhaps if you had some sort of salty snack, it would have interacted with that. Maybe you saw a neon sign that could have had some xenon in it, or if you check the time at all today, there are a lot of atomic clocks that are based off of elements like cesium. But more broadly speaking, so we have this full periodic table here. What exactly do I mean by these heavy elements? So I gave you a few examples before, but generally speaking, I mean pretty much anything that is heavier than element number 26, iron. And so this includes everything basically on this entire bottom part of the periodic table, going all the way down to these lanthanides and actinides here, which will become very important in the talk later. And so to begin talking about exactly how these elements came to be, we first need to understand how we got here. And so how do we go about beginning to figure this out? Well, we can begin to consider things like what can we see around us? And so we can see things like what our sun is made out of, what the Earth is made out of, meteorites that have come here, other stars, other planets, all of that kind of stuff. And as astronomers, we can begin to count up how many atoms of each different element there are in these objects. And so here I have a plot that is showing, as a function of atomic number, how many atoms there are of a particular kind of element compared to hydrogen over here. And so this is a logarithmic abundance plot. And so this is saying that for every trillion hydrogen atoms, or 10 to the 12, there's something like about 100 million carbon atoms, just shy of 100 million iron atoms. And then as we get to our heavy metals down here, there's something like between 10 and 100 lanthanum atoms, about 100 neodymium atoms. And so we can begin to do this for all the different objects that I mentioned before. And a very curious thing happens. While there's a lot of variance in the elements prior to iron, pretty much everywhere that we look, the abundance pattern of elements heavier than iron is exactly the same, no matter where we look. In the Earth, in the stars, in meteors, it is everywhere. And so the question to answer is, how does this pattern appear everywhere? And so to start answering this question, we first can consider, well, how do we start making some of these heavier elements? And we can start off with the simplest one, hydrogen, because hydrogen is constantly being converted into a heavier element, helium, in our universe. In fact, stars all over the universe are doing this at an incredible rate. They do this through nuclear fusion, where they take 4 hydrogen atoms, smash them together. This releases some energy that ultimately goes on to be the sunshine that we observe, and out comes a helium atom. And so this takes some energy, because we need a very high temperature in order to smash together these protons, because they're all like charges, and so they repel each other. And so that's why at the very center of our sun, it is incredibly hot in order to overcome those Coulomb repulsions so that the hydrogen atoms can come together. And we can continue to do this. We can take some helium atoms, smash that together, make carbon, smash some more carbon atoms together to make oxygen, then neon, magnesium, and so on and so on and so on and so on. It just requires increasingly hotter temperatures because there are more protons that are in the nucleus of each of these atoms. And so that requires hotter temperatures in order to overcome that Coulomb repulsion and smash the elements together. And so can we just keep doing this all the way until we get the entirety of the periodic table? Unfortunately, no. We can only go all the way up to iron. And this is because iron has the very unique property that it is the most tightly bound nucleus per nucleon. And so this is why whenever we smash together hydrogen, it releases energy, because the 4 hydrogen protons come together and are bound together, and that energy of binding is released as the light that we ultimately see. However, when you go beyond iron, they're less tightly bound. And so that means you have to put energy into it in order to fuse the heavier elements. And so essentially, when a star starts forming iron in its very core, it is a death sentence for that star, because it will instead start absorbing all of that energy, and the star will collapse in on itself. So if we can't do anything heavier than iron with stars, we have to find another way to go about doing this. And so the answer is the other half of the equation. We've largely been talking about protons here, but we haven't been considering neutrons. Because adding neutrons is quote-unquote a lot easier because there's no Coulomb forces that we have to worry about here. And so if you add a neutron to a particular element, then it is possible that that element is now radioactively unstable. And so what will happen then is that neutron will instead spontaneously decay into both a proton and an electron. And so that's critical, because essentially, without having to overcome any Coulomb forces, you've just snuck a proton into a nucleus and made a heavier element. And so the name for this particular process is called beta decay, where you convert that neutron into a proton. And so if you've just successfully made a stable element, then congratulations, you now have a heavier element that we need to make. And so you can do this in two different regimes. One, where you can slowly drip neutrons onto your nuclei, one by one, waiting for the beta decay to occur. And this is what we refer to as the slow neutron capture, or S process. Or you can go on the opposite end of the spectrum, where you unleash a fire hose of neutrons onto these nuclei, and you add them so quickly that beta decay cannot occur in time. And this is what we refer to as rapid neutron capture, or R process. And so I want to show you an animation of some material that is undergoing R process. And so here we have on these two plots, on the x-axis here is the number of neutrons, and the y-axis here is the number of protons. So every row here is a different element, and every column is a different isotope of that element. The black dots that are here show what elements are stable, the ones that we interact with in our daily lives. And then the color in here shows what is actually in the simulation at this particular time step. And then the top panel over here, on the x-axis, shows the total number of protons plus the number of neutrons. And then the y-axis is how much of that particular combination there is in this simulation, with the red line showing what there is currently, and then the blue dots showing what is in the sun. In the sun. And so the simulation starts, we add up a whole bunch of neutrons, and you can see that the material has moved farther up here, added a whole bunch of neutrons. And as time goes on, you see it slowly starts shifting up and to the left. This is because it's undergoing beta decay. It is converting a neutron, so it's losing one neutron and moving to the left, and converting into a proton and gaining that, so moving up by one. So in total, moving up and to the left. And so as the simulation moves on, you see everything is moving towards all of these black dots. And by the time that we reach the end, critically, we see that up here, the red line matches the blue dots, what we see in the sun, incredibly well. And this is the key. This is what we call the universality of R process, because any time that any material undergoes R process, you produce this particular abundance pattern of elements. And so this is what we see all over the universe, the pattern that repeats itself over and over and over. And so the question now becomes, where in the universe do we have R process? And so that's where my research comes in. I particularly study what are called kilonova. And so these kilonova are these very fast-evolving ultraviolet, optical, and infrared transients that are powered by the radioactive decay of these R process nuclei. And so, just keep in mind that as these elements were all beta decaying up and to the left in the previous simulation, they're releasing energy. And that energy can go into powering an astrophysical transient that we then observe. And so the reason that R process occurs is because these things arise from the merger of two neutron stars, which are very neutron rich and have conditions ripe to be able to unleash that fire hose of neutrons. We also think that it's possible that these could come from neutron star and black hole mergers, but we have yet to observe that. And so normally we talk about our kilonova as having two components, a red component and a blue component, where the red component we normally associate to having a more equatorial geometry, meaning that a lot of the shrapnel that comes from the collision is spread out in the orbital plane of the two neutron stars. And this material usually has very heavy R process nuclei. Compare that to the blue kilonova, which we usually associate to a polar geometry, and usually is made up of a lot more light R process material. And so, here at Berkeley, graduate students have what is called the qualifying exam, where we have to come up with a research roadmap, essentially, for the final years of our PhD. And we have to do a lot of studying, reading the literature, and whatnot. And so as I was doing this, I noticed, as I was reviewing all the literature for my qual, I noticed that there was a consistent problem that was happening in a lot of our kilonova models. And so you can see it here, where all of the dots are actual data that we have, and then the lines are what our models predict. And so this is what is called a light curve, which is looking at how much light of particular wavelengths there is as a function of time. And so you can immediately notice that these bluer colors here fade way too quickly compared to what we see with the actual data. And this is something that is prominent across many different radiative transfer codes, atomic datas, and so the question is then, what is causing this? Because what was very strange is that while there was this very interesting difference here in the optical light at early times, the bolometric luminosity, or the total amount of energy that is released by this transient, was actually tending to be accurate. And so this pointed, as I was reviewing for all of my qual stuff, to the suggestion that the opacities in a lot of our modeling was simply too high, where opacities are a measure of how difficult it is for light to travel through something, a particular medium. And so coming back to the beginning of this presentation, when I mentioned the lanthanides for later, they are very key because the lanthanides dominate the opacities. They are the main contributor. And so this is because when we look at our lanthanides, the reason that they're actually at the very bottom of the periodic table is because they have their valence electrons in the F shell. And the F shell is this incredibly complex electron shell that has countless transitions. And you can see that in this particular plot here, which is showing your number of protons on the x-axis, and then the energy levels of various of the electron levels. And the color corresponds to the density of how many levels there are. And you can immediately pick out the lanthanides right here. It is entirely a consequence of having this valence F shell electron. And so the consequence of having all of these incredibly dense energy levels here is that they are incredibly opaque at these optical and UV wavelengths and tend to reprocess a lot of emission to the infrared. And so this is what gives rise to what we call our blue and red kilonova, because the red kilonova has a lot of these lanthanides that will reprocess the emission into redder wavelengths, while the blue kilonova doesn't have that many lanthanides, and so it will not reprocess emission to those red wavelengths. And normally we talk about this as the lanthanide mass fraction, or xlan. That's how we typically parameterize this, with typical values for a red kilonova component being comprised of about 10% by mass of these lanthanides. So we now understand that our opacities are likely to be too high, and it's a result of these lanthanides. So how do we go about solving them? Well, one potential option is that we can reduce these optical opacities by ionizing them. And so when you ionize an atom, that will stretch out all of the energy levels, thereby increasing the amount of energy a photon needs to interact with that light, which means it will push a lot of the opacities from our optical wavelengths into the UV. And so what's very key about this is that a lot of the simulations that have been done previously assume local thermodynamic equilibrium, or LTE. And so this is where we assume that the temperature of the gas that is emitting is the same as the temperature of the photons, is the same as the temperature of that determines how the electrons are distributed within those energy levels. And so the reason that we do this is because it's very computationally efficient. There are a lot of easy equations that we can write down. It's very easy to simulate. But the problem is that that doesn't necessarily capture all the physics, as we can see, as I'll get into later. And so we naturally expect this ionization above this LTE from all of these decaying R-process elements, because as they decay, remember, they're undergoing beta decay. And so the neutrons are being converted into protons plus electrons. And these electrons are being spit out at very high energies, and they crash into nearby atoms and impart some energy into those, into their bound electrons, and thereby liberate those electrons and ionize those materials. And so, if we write down an equation for how often our process elements are radioactively ionizing material around it, then we can begin to understand where does this effect become important. And so first of all, it will become important once our radioactive ionization is stronger than other ionizing rates. And so the most dominant ionizing rate beyond radioactive ionization is usually photoionization, where a photon comes in with a correct amount of energy and liberates an electron from its atom. And so what we can do here is we can ask, what is the ratio of our radioactive ionization to our photoionization? And we can do that because we can associate a temperature to a particular photoionization rate. Because when material is very hot and dense, it will radiate as what is called a black body. And that the black body function is what is described by local thermodynamic equilibrium. And so when we have a given temperature that's associated to a photoionization rate, we can then ask for some particular given radioactive ionization rate. Where does this ratio become larger than 1, hence radioactive ionization larger than our photoionization? And because as a material gets hotter and hotter, it produces more of those ionizing photons, that means that as it cools, it will produce less photoionizing photons, and there's going to be a critical temperature below which the material is no longer producing enough of these photoionizing photons, and radioactive ionization will become important. So this points to we need material that is very cool in order for radioactive ionization to overtake our photoionization. Then, once our radioactive ionization becomes the dominant ionization rate, then it has to compete against the recombination rate. How often an electron will find an ionized atom and recombine. And so if our recombination rate is too high, then the atoms are going to be constantly going into those lower ionization states, and no matter how strong our radioactive ionization is, if the recombination rate is higher, it will not ionize the material above what we would get out of LTE. And so we can play the exact same game that we just did with the temperatures, except our recombination rate most strongly depends on the density of the surrounding material. And so we get the exact same thing once again, except this time it is a critical density, that below which our recombination rate is not strong enough in order to offset the radioactive ionization rate, and you get a strongly ionized medium. So now we know that in order for radioactive ionization to become important, it needs to be a cool and not very dense part of the ejecta in order for radioactive ionization to strongly influence the ionization state. And so what does this look like? It looks like this. So here on the left, I have what you get if you assume from local thermodynamic equilibrium, and on the right is what you get when you include radioactive ionization. And so what this is showing is, as a function of time along the x-axis, what the dominant ionization state of the ejecta is. And so essentially, you can either look at it as every column here is a snapshot of the entire ejecta at a given moment in time, or if you look at a particular row, that is following along with a particular parcel of gas and looking at how it changes over time. And so the color corresponds to what ionization state is dominant in the ejecta at that particular moment. And so you can see here that for the most part, these are very dark colors, indicating that about 100% of the ejecta is made up of that particular ionization state. But crucially, it is incredibly different from what we see over here when we include radioactive ionization. Most notably, there are two properties that are particularly different. One, that there's this inverted ionization structure, where this green corresponds to triply ionized material, blue is doubly ionized, purple is singly ionized material. And normally what we expect when we assume LTE is that the most highly ionized material is going to be deepest within the ejecta at the slowest velocities here. But here with our radioactive ionization, you get the complete opposite of that. And then the other key component here is that none of these colors are as dark as we had when we assumed LTE. Because with LTE, you pretty much get, for a given combination of temperature and density, one particular ionization state that dominates. Rather here, with radioactive ionization, you'll notice that the colors are a lot lighter, And so this means that there's a mixture of different ionization states in the ejecta. So for example, this material down here is something like 50% singly ionized material, something like 30% doubly ionized, and maybe about 10% neutral and a little bit of the quadruply ionized material. And so you get this very blended ionization state, which is very interesting. And so how does this actually affect what we might observe? Well, so here I have from some of my simulations, again, some light curves for different colors of light. And so the darker, thicker lines correspond to what happens when you include radioactive ionization, and then the thinner lines correspond to assuming LTE. And so again, you can see here that for some of these optical bands, like this red and green line down here, you'll see that when you include radioactive ionization, the light curves here last a lot longer than if you just assume LTE. You can see it is fading way more rapidly when you assume LTE compared to when you include radioactive ionization, where it is much brighter at much later times. And so to kind of more emphasize this point, we can compare this to real data here, where all of these X's are the same data that I had showed you previously. Now, this is not a fit to this particular model, but this really emphasizes just how much better we can do when we include this radioactive ionization. Because you can see that, for example, this green line here actually overproduces what we observe with some kilonova. Same with this red line here, which is the complete opposite of the problem that we had before, where for the exact same ejecta, when you assume LTE, it fades way too rapidly and vanishes well before any of the data would say it does. And also, very critically, you get a lot less of this infrared emission up here. And so that'll actually be very helpful to better quantify the amount of heavy elements that we have in the ejecta here. And so to conclude for this, essentially, I'm putting up a series of spectra here that are showing, again, in the darker lines, what happens when you include radioactive ionization, and the lighter lines when you do not include this and you assume LTE. But crucially, you get a lot of this longer lasting optical emission that better matches all the data that we see. And so with these better modeling, you can actually better estimate how much mass there was, what the heavy metal content of these kilonova were, and you can better predict how exactly the ejecta was launched from the collision here. And so there's a lot more work that I hope to do coming up with all of this radioactive ionization stuff. So stay tuned for more papers, and thank you so much for listening.